Welcome everyone to lecture 7. Today we'll be talking about divide and conquer, merge sort, and master theorem. This is the first topic where we're going into material that might be actually brand new for a lot of you. I mean, we're going to cover merge sort, which hopefully some of you have seen before. But divide and conquer is an algorithmic process or technique that actually allows us to write many different algorithms for many different kinds of problems. And so we're going to go and see how it can help us in sorting, and then we're going to see what properties we have of divide and conquer that we look for every time we're looking at a divide and conquer algorithm. So essentially today we're going to go over kind of why we care about divide and conquer by looking at log of n algorithms. We're going to go ahead and look at the definition of divide and conquer, check out some examples, look at the time and space complexity of a divide and conquer algorithm. We're just going to stick with the basics today. We're not going to look at any crazy ones. We're going to look at one example and then merge sort, and then we're also going to look at some examples of what divide and conquer is not. And then once we go and dive deep into merge sort, we're going to go afterwards and try to find the runtime and the space complexity of it. Two different ways. We're going to do it just manually, step by step, trying to reason things out. And then we're going to also take the last about 10 to 15 minutes or so and cover master theorem, which is a way of analyzing divide and conquer algorithms. All right. And then we'll have takeaways. So if you have any questions or concerns, as always, feel free to ask in chat and I'll be answering them as soon as we can. But let's just start with a silly algorithm, right? So I've given you an algorithm here which takes in a positive integer n, and it's going to output by printing out n over 2, n over 4, n over 8, all the way until it goes down to 1. And here's how it does it. It calls print, right? It just prints the current n and checks to see if n is greater than 0, then it's going to go ahead and make a recursive call. And then what I want you to do is figure out what the runtime of this algorithm is, right? So if you looked at the previous slide, it should already be some huge hint here about what the runtime here is. But I want you to think about not only the runtime, but what the reasoning behind that runtime might be. What do you think proves that your runtime is correct, right? That's what you're expected to do this week in homework for homework 2, which is out and due on Thursday. So I'll give you 20 seconds of silent thought to let you do that. All right, go ahead and type in chat. What do you think the runtime here should be? Okay, we got a vote for in login. We have a vote for login. Some people are saying it's in, but a lot of you are saying that it's login. And I'm curious, like, how do you realize that this is login? The answer is login, but one thing that I want you all to be thinking about is why do you think this might be a login? Beyond just the hint that I said earlier, where this is probably login because we're starting with a login algorithm. What does that even mean? Keeps dividing in half. Exponents but backwards, divide by 2. It halves every run. Remaining work is divided. All right. Yeah, that's some really great answers we're seeing in chat here. All right. So we're seeing basically that if we call silly of 16, right? Here's an example. The next thing we're going to do is we're going to print 16 out. That's the first thing we'll do. And then we'll check to see if 16 is greater than 0. Since it is, we're going to go ahead and call silly on the floor of 16 divided by 2, which would be silly of 8. Right, so we went from 16 to 8, so we've halved the problem. The original problem was this number 16, and we've taken 16 and made the problem smaller by half. We'll do the same process here. We'll check to see if, we'll first print out 8, and then we'll check to see if 8 is greater than 0. It is, so we're going to go ahead and call silly of 4. Silly 4 is going to go and call what? Type in chat. What's the next recursive call that gets made here? Right, this is relying on your knowledge of recursion. So if you feel a little bit rusty on this, please go back and review the recursion lecture and also come to office hours if you're not sure what's going on here, because this is pretty fundamental information and you'll want to know it for the exam soon. All right, so everyone's saying silly of 2, right? Following the pattern here. And we know silly of 2 will call silly of 1. And will we call silly of 0? I'll give you 5 seconds. Does silly of 1 end up calling silly of 0? Yes or no? We have some yeses. We have some nos. I think we're seeing slightly more yeses, but it's actually a flip-flop. Like a lot of people are saying yes, a lot of people are saying no. If we call silly of 1, we'll check. We'll first print out 1. Then we'll check to see if 1 is greater than 0. And since it is, we're actually going to call silly of 0 here. Okay? So floor, if you don't know what that function does, just takes a decimal and rounds it down. So if we have 1 divided by 2, we'll get 1/2. Rounding that down gives us 0. And so we'll call silly of 0 because of the floor function. In Java, the divide automatically floors it if you are working on integers. But in pseudocode, we have to be more explicit, which is interesting for some of you. And what you need to notice is that we have 1, 2, 3, 4, 5, 6 calls, right? If we had a larger argument to silly, if we had, for example, silly of 16, sorry, silly of 32 here. Silly of 32, the first call it's going to make is what? What's the first call it's going to make? And how many calls overall are we going to make to silly if we do silly of 32? Yeah, the first thing we're going to do is call silly of 16. And then we're going to call silly of 8. And we're going to go through the same pattern as we did up here, right? So essentially, every time we double the amount of the input, so we go from 16 to twice of that, the number of recursive calls we make doesn't double. It actually stays pretty stable. So the observation we're making here, as we increase the size of the argument by double, the amount of recursive calls only increased by 1. All right, that pattern is O of log n, where n is the integer in here, right? That pattern is characteristic, I should say, of O of log n, which means that as we increase the n that comes into silly, we could say that silly is 128, but the number of recursive calls we make stays pretty small. It stays under 10. The observation here is that as we increase the size of the argument by double, the amount of recursive calls only increases by 1. The other observation is the number of recursive calls is equal to roughly the total number of steps we'll take. In other words, if we can figure out the number of recursive calls that we make in this example, then we can figure out the runtime. Because the amount of work you do at this recursive call is constant, which means that we only need to count the number of recursive calls necessary in order for us to figure out the overall runtime. The yellow is tough to read. Is it better now? It looks like it sounds like it might be better now. Okay. So the overall runtime is log of n because of this observation we did with this example. Essentially, log of n algorithms are really good. They're really effective because as you see, it doesn't matter how big of an argument we put in, the number of steps we take in order to process that argument and complete the algorithm on the argument is relatively small. It's even better than O of n, which is typically what we would consider effective. Okay, people are saying that when it's yellow on white, it's hard to read. I'll try to type faster. Usually when I'm typing, you'll have that weird highlight. I didn't know if it showed up on yours. It looks like, generally speaking, I have to make sure that I exit out before I move on, so that I finish typing, let you see the white, the yellow background, and then check that out. All right, so the observation we're making is that when we're taking a problem, and a lot of you mentioned this. A lot of you mentioned that we're taking the problem and we're cutting it down by half, right? We're taking the original problem, we make it go from 16 to 8, 8 to 4, 4 to 2. It gets smaller by 1/2 each time. So when we cut down the problem by some multiplicative factor, we oftentimes get a fast algorithm. That's kind of the root of all of the other things we're going to talk about today. So if you know that when we take a problem and we cut it down, let's say we had one whole problem and then we cut it down so we only had to deal with half of a problem, That's good, right? That's really, really good when it comes to writing recursive algorithms. It's something we really want. How do we differentiate between n over 2 runtime or log n runtime? So in that case, if you want to differentiate between n over 2 runtime, so n over 2 runtime, I'm just answering the question in chat. If you have n over 2 runtime, that's n o of n. In other words, the number of steps you take grows linearly with the number of the size of the argument. Right? So if your argument is like, let's say 50, then maybe you take 25 steps. If your argument is 100, maybe you take 50 steps. If your argument is 1,000, maybe you take 500 steps. That's what n over 2 would be. Now, log n is its own class of function. Log n is n O of log n, and you can't really compare it with n over 2, right? Don't confuse the n over 2 here with the runtime, because this n over 2 actually leads to this silly's function runtime to be in log n. In log n rather. So this should be like silly is in O of log n. And in this case, the pattern is that if we have, for example, 128, or sorry, we had 16, that'll give us 6 steps. 32 gives us 7 steps. 64 gives us 8 steps. 128 gives us 9 steps. Right? It's very efficient in comparison. Here we have 100 gives us 50 steps. 128 here just gives us 9. So if we call silly of 17, it makes the same number of calls. When you double the n, then the number of calls increase by 1. Yes, that's exactly right. If we did silly of 17, the math will be a little bit uglier, but it will do roughly the same number of recursive calls as if we did silly of 16. All right, great questions. I really appreciate all of these questions. All right. Like I said, lecture is here for questions. You shouldn't ever feel bad just because you don't yet understand something. And I really appreciate the questions that I'm being asked right now. So thank you for asking them. Let's go ahead and take a look at the definition of divide and conquer. Someone asked, is the runtime including the call to 0? Yes. I mean, the call to 0 is just one more recursive call. So there's actually the difference between log of n plus 1 and log of n minus 1 and log of n doesn't really matter because we drop the trailing terms. So if I'm off by 1, counting the number of recursive calls, if it's actually log of n minus 1 or log of n plus 1, we don't really care when it comes to finding the runtime. All right, so let's talk about divide and conquer. Divide and conquer is a pattern in recursive algorithms that has 2 defining characteristics. When I say pattern, I mean that it's not an algorithm in itself, but it is something that you see happen in recursive algorithms over and over again. It has the first thing is at each step, there are 2 or more recursive calls. And the second thing is that the problem is being reduced by some multiplicative factor at each call. So if there's only one recursive call, it's called decrease and conquer. This is a blue slide, blue background, which means that you should strive to memorize this, write this down. Even if you're going to look at the slides later, it really helps you remember things and understand things when you actually write them down. It's just fundamentally better for your brain. All right. A lot of cognitive scientists want you to like read this over, write it down, and that they say will help you remember. And based on my experience, it's true. All right, so divide and conquer is a pattern in recursive algorithms that have 2 defining characteristics. There's 2 or more recursive calls at each step, and the problem at each step is being reduced by some multiplicative factor, right, at each recursive call. So we're just going to go ahead and try to apply this definition to some functions we're going to see. The first function we're going to see is this one from before. Is this divide and conquer? I'm going to give you about 1 minute to try to think about this, and also vote on whether or not you think it is. All right, so we're going to go ahead and launch the poll now. You have about 1 minute. And again, these polls are here to just help you think. You can say yes, no, or that it's decrease and conquer. And the goal here is to get everyone to vote, even if you don't have a 100% sure, 100% sure answer. We want you to be able to think about it and exercise the muscle of reasoning through this definition. And we also want to see where the class's overall opinion is at, right? It really helps me teach, decides on whether or not I should go faster or slower in class. So you have 30 seconds left. I'll just be quiet for this next 20 seconds. Please go ahead and think about it and then make your vote. There's about 10 of you left who haven't voted. I'll give you about 10 seconds to wrap up here. Again, you should never be feeling bad just because you don't know the answer. You're never measured on whether or not you get this correct, right? So we just want you to get your vote in so that I get a sense of where the class is at. So if the class is all picking the right answer, maybe I don't have to spend as much time explaining it and we can move on to the next thing. If everyone gets confused and vote the wrong answer, then obviously we want to explain it in more detail. There's about 5 of you left. Go ahead and finish your votes if you haven't already. I'm going to close the poll now. All right, so it was a tight race. About half of you thought that this was decrease and conquer. And then some of you thought that this was divide and conquer. And some of you thought that it was not divide and conquer. Let's go ahead and take a look at our definition here. It says at each step, there are 2 or more recursive calls. In this case, I can only see the one recursive call being made here, right? So since there's only one recursive call, we already fail this definition here, right? So this definition, the first part failed out. Is the second part true though? Are we taking a problem and dividing it by some multiplicative factor? So in other words, if we have some initial argument that is of size n, are we making it in the recursive call a problem of size n over 2? In this case, yes, right? We are taking the problem, we're cutting it down by half at each recursive call, as we saw in the previous example. Now, given that there's only one recursive call, it's definitely not divide and conquer, but we see down here that there's a definition that says if there's only one recursive call, then it's called decrease and conquer, right? So all we're doing right now is playing with definitions. Type silly in chat if you feel good about this slide and why this is decrease and conquer. Type question mark if you feel like you're a little bit confused and you need me to repeat something. Okay, most of you, actually all of you so far are typing in silly, so I'm going to move on. You can always tell me to go back and answer or repeat something and review something. You should never feel bad if you're like the only person typing in question mark. I definitely will stop for you either at the break or we can, if there's time, talk about it in lecture or in office hours if you feel like that might help. Are all recursive solutions divide and conquer? We're about to see. Here's another example here. Someone asked, in this case, is log of n base 2? Yeah, so when I say, sorry, one thing that should be important to note is that when I say log of n, I don't really care about the base, especially if we're talking about O of log n. If we're talking about O of log n in particular, the base actually doesn't matter because of the change of base formula you'll see in later on. So if you say O of log n here, we don't care about the base of what log n is. So it could be base 2, it could be base 10, it could be the natural logarithm. That's a great question. In the previous example, we were talking in terms of log base 2. But again, once we talk about big O, the base doesn't really matter. All right. And that's something that is important to know. It comes from math. You can actually change the log into any other log if you use the change of base formula. And if you're not sure what that means, go ahead and review the Big O and runtime practice worksheet. That's super important. In fact, the question that we're about to solve comes from this worksheet. And this worksheet has all of the answers to all of your questions. For example, you just highlight over a section here and you'll get the actual answer. And you see, I've actually gave you the hint of the change of log rules to see why this, for example, is true. That log base 2 is in big O of log base 10. And then, you know, for other problems, there are solutions in much detail here. Okay, so let's go ahead and come back to this. I'll ask the same question. Is this divide and conquer? Is this not divide and conquer? Is this decrease and conquer? You'll have about a minute and 20 seconds. Okay, most people are voting pretty fast in this case. There's about 20 of you who still haven't voted, a little bit less than 20 now. Let's go ahead and wrap this up since everyone seems to feel a little bit more confident about this. About 7 of you left. I'm really happy that everyone seems to be mostly getting it. So if you feel a little bit sure about this, that's great. If you're a little bit confused, that's okay. We'll go over it. All right. So it seems in this case, most of you thought, about 75% of you, a little bit more than 75% thought that this was divide and conquer. In this case, we have a algorithm that does have these two characteristics, right? So we have two or more recursive calls. In this case, we have exactly 2, right? We have a call to quandary 2 here and a call to quandary 2 here, right? So at each step, there are 2 more recursive calls. We can check that up. And then the problem is being reduced by some multiplicative factor, just like we saw in silly from before. So this is also true, right? So is this divide and conquer? The answer here is yes. Right? The previous section was no, it was decrease and conquer. And this section, this slide here, is yes. Quandary 2 is a divide and conquer algorithm. What would be the runtime in this case? It's a great question. We're going to look at it in about 3 slides or so. So hang on tight to that question. Aditya, that's a really good question. We're going to cover it in more detail afterwards. All right. So we're just going to continue on and label more functions, divide and conquer and not. And then we'll go back and answer that question of what the runtime of it should be. All right, let's take a look at this next algorithm. Go ahead and start thinking about it. I'll relaunch the poll. You'll have about 1 minute here so that we can move a little bit faster since most of you feel comfortable with this according to the poll results. All right, about 15 of you need to vote, and we have 30 seconds left, which is good. Again, just give it your best thought. The important part is that you think about whether or not the definition here applies to this algorithm. And if you are still a little bit confused, think about why it is you're confused, right? The whole point of this class is to help you learn. So if you're not doing any thinking right now, you're not really using this opportunity to learn, which is why I always try to emphasize it every single time. All right. So a lot of you finished voting here. Thank you so much. Most of you thought it was no. About half of you thought it was no. About more than a third of you thought it was yes. And then some people thought it was decrease and conquer. So let's look at this in detail. Are there 2 or more recursive calls in this case? Yes or no? Type it in chat. Yes, right? Because there's 1 call here and 1 call here. So by definition, it can't be decrease and conquer. We're already in a place where decrease and conquer can't be true. Now, the second question is the problem, or the second characteristic is that the problem is being reduced by some multiplicative factor at each call. Multiplicative factor, if you remember, means dividing by 2 or dividing by 10, taking a problem of size n and making it smaller by some multiplicative factor means that you take the problem, let's say there was 100 apples before, and then if I eat half of them somehow, miraculously eat half of them all at once, that's taking the problem and cutting it down by half, and that is a multiplicative factor. If I took 100 apples and I only ate 1 of them or 2 of them, then it would not be a multiplicative factor because I didn't make the problem smaller enough for it to be considered a multiplicative factor. So in this case, Fibonacci is closer to the second example I just gave. We only take n and make it smaller by 1 or 2 at each recursive call. So we're not able to cut the problem down fast enough in order for this to be considered a multiplicative factor. Now, for numbers, usually that means you're dividing the number by like 2 or 3 or 10 or something. For lists, you might be making a smaller list. For other data structures, you might be also finding some way to take that data structure and only observe maybe a half of it, a fourth of it, stuff like that. All right. So in this case, is this divide and conquer? No. it's also not decrease and conquer, right? So it's no across the board. If you have any questions, feel free to ask now. We're going to move on, but I can always come back. One last one here. Yeah, I think this is the last one. I'll give you about 1.5 minutes. No, sorry, just 1 minute to think about this. This is quicksort from last lecture, right? We want you to think about quicksort in this case. This is the second to last one. There's actually binary search after this. So if you don't remember this algorithm, this is quicksort, and we went over it at the beginning of last lecture. So hopefully this seems at least a little bit familiar. We went over the runtime, and we also went over how this function works step by step. So this is really just applying what you learned last lecture in a new context, taking what you understand of quicksort and applying the definition of divide and conquer on it, right? You see, I'm taking care to explain to you the levels of learning I expect you to do here. Hopefully you're feeling comfortable. There's about maybe 15 of you who still haven't voted. Let's go ahead and wrap this up so that we can move on. So if you haven't voted already, give it your best guess. All right. So about 60% of you thought this was a divide and conquer. About 28% of you thought it wasn't. And then some of you thought it was decrease and conquer still. Now let's go ahead and rule out decrease and conquer. It can't be decrease and conquer because of what? I'll give you 10 seconds in chat. Why can't it be decrease and conquer? What line in this code tells me that it's not decrease and conquer? All right, people are saying last line because we have two calls to quicksort, one on for the left list and one on the right list, which means that there's not more than one recursive call. We can already rule this out. Now, the tricky part here, after you ruled out that this is not decrease and conquer, is that are we sure that this is divide and conquer? 60% of you said yes, but I'm not sure if this is 100% true. Let me think about it. Think about it this way. In the worst case, is quicksort divide and conquer? In the worst case, when you pass the worst possible argument to quicksort, is it divide and conquer? In the worst case, what happens is we'll pass in a reverse list, right? A list that is already sorted, let's say. And then if we already sorted, that means that the left-hand side list will contain everything that's smaller than the pivot, in which case is literally n-1 elements. And then the right-hand side will contain 0 elements. That's what will happen if we pass in a list that's already sorted. So assuming we pass in a list that's already sorted, we covered this last lecture. So this is just remembering what we talked about last lecture. That means the left list will have n-1 elements, and the right list will have 0 elements. That's no good, right? In this case, this runtime would be n squared, but also n-1 is not reducing the problem by a multiplicative factor. So in the worst case, no, it's not, right? Like the divide and conquer algorithm, quicksort is not a divide and conquer algorithm in the worst case. So depending on what inputs you put into quicksort, you actually can say yes or no to quicksort. In the best case, and also the average case, is quicksort divide and conquer? Based on what we just talked about, if we have a list that's already sorted, this is the worst case, and the answer is no. If we pick the perfect pivots, right? So remember, I made a big deal of saying that we can pick the perfect pivots for this partition. Assuming we pick a list that has perfect pivots at each partition, then this will become n/2 elements instead, right? And then this will also be n/2 elements. And if that's the case, then we're splitting the problem down by half each time. We can say yes here, right? We can say, yes, in the best case, in the average case, quicksort is divide and conquer. Now, in the average case, we don't always pick the perfect pivots, but it's so unlikely for you to pick the worst possible pivot at each and every stage that on average for a random list, you're probably going to be good, which is why quicksort is actually so fast, right? So this was a more nuanced question. A lot of you said yes, but I hope that you also thought about the worst case where the answer is no, right? And this type of detail in understanding your sorts is what I expect of you on the exam and going forward. So let's take a look at one last algorithm. In this case, it's called binary search. And some of you might have seen this in the past, some of you might have not. I'm going to explain what this code does afterwards, but for now, just do your best to try to read it and understand it. Again, the definition here of divide and conquer, I'm not going to show you on this slide either. This is really kind of like a mini popped quiz with no stakes, right? It doesn't matter if you get this wrong, but I want you to use this as a way to show whether or not you actually understand this now, right? To show yourself if you actually understand what's going on. So I'll give you 30 more seconds to think about this on your own about whether or not this is a divide and conquer algorithm. So I'm going to ask, so divide and conquer only applies if there's a multiplicative reduction in any case. You have to make sure that every time you make a recursive call, the problem is getting reduced by some multiplicative factor. If one of your recursive calls only reduces by some like linear factor or some single constant factor, then you're not going to be able to call that divide and conquer. All right, there's still about 10 of you who haven't voted. Please do so now. All right, this one was much tighter. Almost everyone was evenly split between yes and decrease and conquer. And then some people thought this was not decrease and conquer and not divide and conquer. So remember, this is why I asked you to write down the note in your notes, whether or not divide and conquer, the definition rather of divide and conquer. Divide and conquer needs 1, 2 or more recursive calls, and 2, making the problem smaller at each call, right? By a multiplicative factor. That's the definition. I'll write that here in case those of you who were a little bit unsure needs the review. Right? It's not bad that you need the review, but it is important that you study and take notes on your own. That way you can learn the most. All right, so first let's just understand what this function is doing, because right now it's not necessarily clear that we have a good idea. Binary search helper takes in a sorted array list, an integer target x, a left index a, and a right index b. So let's just come up with an example. Let's call this binary search helper. Let's call it BSH for short. And we're going to call, let's make this red so that's easier to read. We're going to call this on a sorted list. So like 1, 2, 8, 9, 15, 200, 301. Right? And we're going to look for the target, in this case, 301. We're going to start with a left index, let's say, of 0 and a right index of 0, 1, 2, 3, 4, 5, 6. All right. So this is the first call we make. We check and say that list is this list here, that the target is 301, the left index A is 0, and the right index B is 6. We check to see if A is greater than B. In this case, it's not, right? Because 0 is not greater than 6. Then we compute the midpoint. I'll give you 10 seconds. What is the answer here to midpoint? What is midpoint if this is the input? Go ahead and type in chat now. It's 3, right? Because 0 plus 6 divided by 2 is 6 over 2, which is 3, right? Nothing too scary. So that means at index 3, that's what this if statement is saying. It's saying that at index 3 in the list, check to see if it's equal to x. So 0, 1, 2, 3 would check this 9. Is it equal to 301? No. So we're going to go ahead and check to see if the midpoint, the element at the midpoint, if it's less than 301. And it is. So it goes and makes a recursive call to midpoint plus 1, which is now going to be 4, right? The next call we're going to call is BSH to the same list. The list doesn't change. The target doesn't change. But the midpoint now changes. The A argument changes from 0 to 4. And then B is still 6 in this case, right? So we've taken the original problem and we've reduced it by more than half. Instead of looking at index 0 all the way up to index 6, we're now only looking at index 4 all the way up to index 6. Why does it only have 3 parameters? Because I made a typo earlier and I still haven't fixed it. Good call out. There should be an X here inside here as the second argument. Good call out. I need to remember to fix it. Why is this 4? Because we checked and saw that at the midpoint, which gives us 9, the midpoint is smaller than the current X we're looking at, which is 301. 301 is greater than 9. Since that's the case, we know that since this is a sorted list, we're going to look on the right side because everything that's bigger than 9 is going to be on the right half of our original list. Given this list here, 1, 2, 8, 9, 15, 200, 301, this is increasing in size. It's already sorted, which means all the big numbers are on the right. So if we look in the middle, realize that 301 is bigger than the middle, then it better be on the right if it's in there at all. So the 4 just describes that now we're going to look, instead of looking from 0 all the way up to 301, we're going to start at 15 and look all the way up to 301, right? We're going to look at this part. So that was a great question. Thank you for asking it. We're going to just wrap this up now. We're going to check again and check the midpoint. This time, the midpoint is going to be 4 plus 6 divided by 2. For that is index 5, which is 0, 1, 2, 3, 4, 5, 200. And we do the same calculation. We say, is 300 equal to 200? Sorry, is 301 equal to 200? It's clearly not. So we're going to go ahead and make the next question, which is 300 going to, is 301 bigger than 200? And it clearly is. So we're going to continue on. And now we're going to go and look for a new midpoint, which is 6, right? Because we had 5 before. The midpoint was 5 before. That's how we got the 200. 5 plus 1 is 6. And then we pass in 6 here as well, right? And I'm just trying to explain step by step how this works. At this point, we've cut the problem down by half yet again, but this half is a little bit smaller, right? Instead of worrying about this entire 3 elements, we only worry about the element on the very rightmost. And then we finally compute the midpoint here, which would be index 6. Check to see if 301 is equal to 301. It is, so we return it here. So we only made 3 recursive calls here. That's pretty dope. Pretend like this says 3. And we realize the observation I need to make is how many recursive calls did we make at each step? Did we make 1 recursive call or 2? We only made 1, right? We would have either made this recursive call or this recursive call, but not both. Since we only make 1, we can't say that 2 or more recursive calls happened. So that's out. But number 2 is true, right? Number 2 actually in this case worked out. If you look at the top right where I'm drawing here, the second characteristic of a divide and conquer algorithm is that we make the problem smaller by half. And in this case, because we look at the numbers, the A's and B's, they're making the problem smaller by half each time. That's what we needed, all right? Which means that this is not a divide and conquer, but it is a decrease and conquer. Binary search helper in this case is a decrease and conquer algorithm. Cool? All right. Now, in the best case, it returns the first time. Yeah, that's true. Let's see. We're good on time, so we're going to take the next slide and we're going to try to think about this, all right? What is the time and space complexity here? Let me go ahead and set up a poll for this because this is actually really important. Someone asked me, hey, are we going to find the runtime of this divide and conquer algorithm? And the answer is yes. We're going to go ahead and try to answer that now. And then afterwards, I'll explain it and then we'll take a break. All right, about 10 of you still haven't voted, so go ahead and wrap that up now. And for those of you who already voted, we have an interesting conversation happening in chat where someone asked, hey, in the best case from before, shouldn't the divide and conquer for binary search, like that's not divide and conquer in the best case because we wouldn't make any recursive calls, right? And I'm like, yeah, that's true, you're right. And would binary search be considered divide and conquer in the best case? I'm not sure, right? It could be yes, it could be no. But usually what we want to just think about is using divide and conquer that property or that definition, that classification in useful contexts. Since in binary search, in the best case, the runtime is O of 1, we kind of don't really care about that case as much. Whereas when we're looking at the quicksort version, the runtime was much worse in the worst case. And it also kind of makes it clear that it doesn't follow the properties of divide and conquer. And that's an observation we find interesting, all right? So that's a really good observation that in the best case, binary search is technically not divide and conquer, but we also kind of don't care, right? In the quicksort case, since we were talking about worst case, and since the worst case was kind of bad, we do care about that a bit more. All right, so let's go ahead and take a look at the time and space complexity here. I gave you a little bit more time since this is a more involved question. People are saying that the best case runtime is O of 1, that the worst case runtime is O of log n, and that the average case is O of log n as well. Space being used is mixed between O of 1 and O of n. All right. So let me just go ahead and try to explain it. After this, we'll take a 5-minute break, I promise. But let's start here, right? Let's start by calling quandary on something like 16. If we call quandary on 16, we're going to check to see if 16 is equal to 1. It's not, so it's going to make 2 recursive calls, right? Go ahead and type in chat, what are the 2 recursive calls that get made when we call quandary of 16? Okay, people are saying call quandary of 8, and then also call quandary of 8. So we have to call at some point quandary of 8, and also quandary of 8, okay? Now, you can already see where I'm going with this, right? We have to call quandary of 8. That means we have to then call, at this point, quandary of 4 and quandary of 4, right? When we're in the middle of figuring out quandary of 16, we also then have to figure out quandary of 8 twice. In the first quandary of 8, since Java can't do 2 things at once, we just go into the first quandary of 8. Let's say it's on the left-hand side here, which it is. Then we're going to go and say n is equal to 8. N is not equal to 1 in this case because 8 is not equal to 1. So we'll go ahead and make a recursive call on the left-hand side and a recursive call on the right-hand side. Now, in order to figure out quandary of 4, we have to make 2 calls to quandary of 2. And let me just make it absolutely clear. We're really just writing down that as time goes on, this is time, right? We're figuring out that time here increases. And as we go on, here are the calls we're going to make at each stage, all right? Hopefully you feel good about this. But if you have any questions, feel free to ask. But after we're done calling quandary of 2 and calling quandary of 2 here, we're going to call quandary of 4 again, because that's what we do in quandary of 8, which means we're going to call quandary of 2 here, quandary of 2 here, right? Oh, sorry, I missed a step, actually. Instead of calling quandary of 2, we're missing doing quandary of 1 here. Quandary of 1 happens first, right? We go from 16 to 8, 8 to 4, 4 to 2, 2 to 1. And then once we're done here, we're going to go ahead and make another recursive call to the other quandary of 1, because in the middle of doing quandary of 2, what we said was call quandary of n minus 2. 2 over 1 is, sorry, 2 over 2 is 1. And the other n minus n over 2. I keep saying minus 2. I mean n over 2 on the left and the right, which means 2 calls to quandary of 1 here. Now we do that as well for the next quandary, right? And then we do all of this as well for the next quandary of 4. And we do all of this as well for the next quandary of 8, right? That's a lot of calls. How many calls did we actually make here if we count this all up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 31. 31 calls were made when we passed in 16. Now, if we were to imagine in this case, just like how we did with Silly, if we did quandary of 32 here, how many calls do you think we would make here? Okay, some people are typing in 64. Some people are typing in 63. So if all of this was what, 31 calls, including the first one here, then quandary of 32 is going to make 2 calls to quandary of 16, which means that there's 31 plus 31 plus the call itself, which gives us 63 total, right? 63 calls, including the initial one, because quandary of 32 will make a call to quandary of 16, which will give me 31 calls, and then another call to quandary of 16, which will give me another 31 calls. And then we also have to count the fact that it counts itself, which is where we get 32 out of, right? So if we get this pattern, that quandary of 16 gives me 31 calls, quandary of 32 will give me 63 calls, and quandary of 64, you can imagine, gives me 127 calls, right? It's not the input squared. It's just Q of n is going to give me n times 2 minus 1 calls. Oh, wait, no, someone gave in, literally typed that in chat. All right, cool. So everyone observed that it's twice the many, roughly twice as much as the initial input. And here, observe, everything besides the recursive calls is O of 1 time, right? So observation that you need to make here, everything besides the recursive calls is O of 1 work, which means we only need to keep track of the total number of recursive calls we make to figure out the total number of steps that we have here. Since the number of recursive calls is 2n, that means quandary here is n O of n, right? That is the best case, the worst case, and the average case in this sense, because we don't actually have any numbers that when we put in will behave any differently than the exercise we just did. All right. So I could draw this another way. I could draw the recursive tree. I could say that we first call quandary of 16, right? And that's going to call quandary of 8. And it's also going to make another call to quandary of 8. You've probably seen this representation in the past. I'm doing a bad job of drawing it. Another way we can draw this is we start with quandary of 16, and then we know that's going to make a call to quandary of 8, and then another call to quandary of 8 later, right? So we know that that's going to happen here, and then we're going to make 2 calls here, and then 2 calls here, and then 2 calls here, right? Every one of these arrows represents another recursive call you're going to have to consider. And you know this branches out a lot, which is similar to what we just saw. We're not going to draw all of this out, but this is something that you typically see when you're trying to look at tree recursion. We did this in the recursive lecture as well, right? So this is exactly a recursive tree, exactly as someone in chat is saying, right? So it's O of n, because we had this observation. We made this observation that as we increase the size of the input, right? When we did quandary of 16, we got 32 steps. We got 32 steps at 16. We got 63 steps at 32. We got 127 steps at 64, which means that every time we pass in an argument n, we're going to get n times 2 minus 1 recursive calls. Since the amount of work being done at each recursive call is O of 1, that means we just multiply n times 2 minus 1 with the amount O of 1 and get O of n at the end of the day, right? 2n minus 1 is still n O of n, which means quandary here is n O of n. Now, we need to also talk about space at the same time. Space here is a little bit more tricky. Let me just make an observation here, and then I promise we'll have a break, right? So just keep tuned in for another 5 minutes, and then you'll have your earned break. I know we are going a little bit longer than before, but this one's really, really important, and I need you all to understand it before we go and switch to MergeSort. Observation. Java remembers a function call if it's not yet complete, right? In other words, if it's active, then we'll remember it. Observation number 1, Java remembers a function call if it's not yet complete. So let's just imagine at the very beginning, we call quandary of 6, right? We're still talking about this example. Quandary of 6 is the first thing we call, and we need to remember that it exists. Since we need to remember that it exists, we need to remember that it exists even when we're doing quandary of 8, right? If we do quandary of 8 here, we still remember that we're in the middle of doing quandary of 16. Type 16 in chat if you feel like you're understanding what's going on. Cool. That means that if we're doing quandary of 8, Java remembers that we're doing quandary of 8 and quandary of 16 while we're doing quandary of 4, which needs to happen because we're in the middle of doing quandary of 8. Java also remembers that we are doing quandary of 4 and quandary of 8 and quandary of 16 when we're doing quandary of 2. Java also remembers that we're doing quandary of 2 when we're in the middle of doing quandary of 1, and so on. Observation number 2, which directly follows from observation number 1, Java forgets a function existed or a function was called as soon as that function returns. This is super duper important. Write this down. I don't have it in slides. I should put it in slides, but this is so important. If you understand observation number 1 and observation number 2, you're in really good shape. All right. What I mean by this is that at some point, we're going to check to see if n is equal to 1, which it is in the case of quandary of 1, which means it's going to output 1 here. Once we returned 1, Java's like, all right, you got your answer, right? We got quandary of 1 outputting 1. So we just forget that we ever made this recursive call. We don't care about it anymore. Which means the number of things Java needs to remember at this stage is 1, 2, 3, 4 things, right? It used to remember 5 things, but now it's 4 because we just got the return value of 1. What's the next recursive call we have to make at this point in time? What's the next step here? Type it in chat if you know. What's the next recursive call we're making? Yeah, we're making another call to quandary of 1 because we only made the first call to quandary 1, and quandary of 2 makes 2 calls to quandary of 1. So the second call here goes quandary of 1. Sorry, that should be a 1, not a 2. That's the second call that gets made. So Java goes back to remembering 1, 2, 3, 4, 5 function calls. All right, type 5 in chat if you understand so far. Java's remembering stuff. Every time you make a function call, you have to remember it. And that costs us space. We're trying to answer the space complexity question right now, right? And then at some point, we're going to be done here. We're going to be done with this quandary of 2. Quandary of 1, which means that it outputted, in this case, 1. And then that means we have 1 plus 1 here for quandary of 2. When we're calling quandary of 2, we can do 1 plus 1 because that was the answer from quandary of 1, and that was the answer from the other quandary of 1, and we get 2 here. Okay? That means once we get a return value here, we're just done with calling quandary of 2. Java only has methods, not functions? Yeah. So technically, if we're saying Java, we're talking about methods, but all methods are functions. Not all functions are methods. Why are there 2 calls to 1? Because when we're calling, when n is equal to 2, we have to make a left call to quandary of n over 2, which is 1, right? Quandary of 1, and this other call of quandary of 1. So at this point, Java has to remember only 3 things. What's the next call Java makes? Go ahead and type in chat if you know. Right? We're in the middle now of calling quandary of 4. We just finished up with the first call to quandary of 2 in the middle of calling quandary of 4. So now we have to go and call quandary of 2 again. Right? Since we call quandary of 2 again, we're going to do this whole song and dance again where we go in and we have to remember up to 5 things. Right? Here's the question. At any point in time, how many things does Java have to remember? How many calls does Java have to remember while evaluating quandary of 16? At any point in time, I'll give you 20 seconds. Think about this for yourself. At any point in time, how many calls did Java have to remember while evaluating quandary of 16? Let me give you a hint here. What we had before, when we traced out every single call, this is what we had before. And some of these will be crossed out, right? Over time, some of these will all be crossed out because at any point that we return from that function, Java will just forget that that function exists. So it no longer has to keep track of it. A lot of you are typing 4 in chat. Some of you are typing in 5. Go ahead and enter your answer if you haven't already. Do you think it's 4 or 5? Add a question mark if you're not sure. It's okay if you're not sure. Does it do one side and then the other? Yeah, it does. Okay, a lot of you are confused. That's totally okay. That's great. I appreciate that you're showing me that you're confused. The answer here is 5. We keep track of 5 because a lot of you who said 4 forgot to keep track of the 16 itself. All right, so let me explain why. At any point in time, Java has to keep track of 16 and then 8 and then 4 and then 2 and then 1. And then at this point, that's 1, 2, 3, 4, 5, right? Let me just go ahead and erase these lines here. Oh, dang. This is going to be hard to erase. 1 second as I get the setup correct. All right. So first off, we start with quandary of 16. Then we go into quandary of 8. And then someone asks, I'm still confused why you didn't call the others twice, but decided to do so on the 1. We did call the others twice. We called quandary of 2 again down here in order to solve quandary of 4. So we called quandary of 1 twice. That meant quandary of 2 here was good. And then we go back to quandary of 4. And when we're in the middle of doing quandary of 4, we have to call quandary of 2 twice. So here's the first one, and here's the second one. That then calls quandary of 2 calls quandary of 1 twice. And then we're done with quandary of 4, right? So let me go ahead and just step through it step at a time, right? Remember, we're going down in time. Going down means we're going through and going forward in time. We start with quandary of 6. Quandary of 16. 16 in chat if you understand what we're starting with, 16, right? We just start with quandary of 16. The first recursive call we're going to make is to 8. Now, once we go and make a recursive call to 8, the next recursive call is going to be 4. Now, at this point, when we're calling quandary of 4, can we erase this 18? Sorry, erase the 8? Yes or no? Can we go ahead and delete the 8? We're getting a lot of no's in chat because, again, we have to remember a function call if it's not yet complete. 8 is still active because we have to answer quandary of 4 once and then twice in order to actually answer it, in order to return from quandary of 8, right? So we're in the middle of quandary of 8 because we're still trying to do quandary of 4. Quandary of 4 calls quandary of 2. Quandary of 2 calls quandary of 1. At this point, quandary of 1 can return right away. So we actually just forget it, right? So up until now, we had remembered 5 things. And then we just erased 1. So now we're up to 4. Then we have to look at another quandary of 1, which means we're back to remembering 5 things. But then we return right away. So we're back to remembering 4. Well, now that we've finished quandary of 1 and quandary of 1, that means we've actually gotten the answer to quandary of 2 because we just add those 2 answers together. Now we're back to remembering 4 things. And we can't go on and cross out quandary of 4 because what is the next call we still have to make inside of quandary 4? Type it in chat if you know. What's the next step here? Quandary of 2. Exactly. So we're now processing quandary of 2 again. So that means we have 1, 2, 3, 4 things we're keeping track of if we include the quandary of 2. We go down deeper and do quandary of 1. Now we have 5 things. We're done with the first quandary of 1. Then we're done with the second quandary of 1. At each point, we're only keeping track of 5 things, right? And so then once we're done there, we go ahead and finish up quandary of 2. So you can see as we're going down, the most amount of calls, the deepest we ever go, right? In other words, the deepest we ever go in the number of recursive calls is 5 calls. Right? We go from quandary of 16 to quandary of 8. Let's say we cross this out and we finish this, right? Then at this point, we would have to go and look at this quandary of 4 and all of its things that we have to worry about, right? But at this point, like at any point, we're only ever going to keep track of 5 things because the deepest we ever go is 5 recursive calls, right? As soon as we're done with quandary of 1, we cross it out. So we never can go any deeper because by the time we get to the next quandary of 1, we already crossed out the previous one. So we maintain a depth of 5. All right. So what that all means is that we remember at most log of n recursive calls at any point in time, which means that the space complexity is O of log n. All right, so the space complexity we just figured out is O of log n because we only remember up to log n recursive calls at any point in time. This 5 looks very similar because we're just keeping track of the number of recursive calls we make. Log of the initial number just gives us that answer of how deep we ever go. And then the time complexity we already said before was O of n, right? Where n is the initial argument in here. All right, that was a lot of stuff to cover. I hope you felt good about this. If you still have questions, feel free to ask on break. We're going to take a 5-minute break now. We'll come back at 3:55 and talk about MergeSort. Someone asked me to go back. We're taking a 5-minute break. If you have questions, feel free to ask now. Now is your chance to kind of catch up and get unconfused about anything you were stuck about in the last like 40 minutes or so. Why was the time complexity O of n? We did a lot of work just counting up the number of recursive calls before. Remember for quandary of 16, we got 31 recursive calls. If we did quandary of 32, we would get 63 recursive calls. And that pattern was 2n, roughly 2n, right? Whatever n we pass in, the number of recursive calls would be roughly twice of that, which meant that the overall runtime is O of n. Can I explain again why we have 2 quandary of 1s? Because every time we're calling quandary, we're going to make a left recursive call to n over 2 and right recursive call to n over 2. At every stage, we're going to make 2 recursive calls no matter what. It just so happens that Java can only do one thing at a time. And so you'll see the recursive calls being split out in a different direction if we're considering time to flow downwards. So the question was, why do we get 2 recursive calls for quandary of 1? I mean, we call 2 recursive calls for every single step here, right? If you look here, quandary of 16 calls quandary of 8, and then also quandary of 8 here. Each quandary of 8 calls quandary of 4 twice, right? And each quandary of 4 calls each quandary of 2 twice. It just happens at a different point in time. It just so happens that you see 2 quandary 1s together because that's the very bottommost layer, which means that they're nested right next to each other because that's the next thing that they'll do. Can you explain what the n in space complexity is? That's the number here. N is defined as this initial input number here. So when we're talking about O of n for the time complexity, that is this n here. And when we're talking about space in log of n here, that n defined here is the same as this n initially. Again, we're on break. Feel free to take the next 3 minutes to go to the bathroom, drink some water, stretch, do whatever it is you need to do. What if for any value n, the number of recursive steps were increasing? Let's see. Shresh just asked an interesting question, but I think what you're saying here, like that pattern that you're showing in chat is already O of n, right? If the number just doubles, if it's double the input, which is what we have here, then it's O of n. In order to show an O of n squared complexity, we would have to see something like Fibonacci. Fibonacci is one example of O of n. And one thing that you can do is also take a look at the examples in this worksheet, which you should definitely do. Quandary, the original quandary, actually gives you an example of a n 2 to the n runtime. One thing that you should note is that we make a lot of recursive calls here, but somehow the runtime is actually still very good. And that's something we'll cover once we come back from break. What if we did return quandary 2 of n over 2? That's a great question. That means that we would half the amount of recursive calls we would need to make at each level, which means that we would actually end up with a log of n runtime, right? So instead of saying quandary of 2 plus quandary of 2 here, or quandary of n over 2 plus quandary of n over 2, if you just said 2 times quandary of n over 2 and made one recursive call at each stage, we would actually reduce the number of recursive calls by a lot, and we would end up with a log of n runtime. It would look a lot like silly. Will we ever use this example with dynamic programming? We'll definitely cover dynamic programming later in the semester. We might come back to this and revisit it accordingly. Okay, someone's asking, what is the log of n units in time in terms of for space complexity? You can think of it as space in RAM. So you can think of it in terms of bytes if you want, but you can just think of it as there's some atomic value or some atomic unit necessary for one thing. If you want to store one thing in your computer, whether it's one number or one function call, that's the unit that we're using. What is the tight upper bound and how do we find it? We covered tight upper bound in class in lecture 4 and 3, but there's actually a post. Someone asked about tight upper bounds in Piazza, which might actually help you a lot. This post is really, really helpful, especially the follow-up. So I would take a look at the follow-up first and read it before you, like if you still have questions, feel free to ask, of course, but we don't have too much time because we're about to come back from break. And the tight upper bound here is defined here. Like we go over some examples and someone provides some really good answers. All right, so that's a good question, but I'm gonna go ahead and move ahead. If you still have questions, feel free to ask me at the next break or ask me after class, but we have to move on now. All right, so the first thing we wanna observe is that even though we made so many recursive calls, the runtime is actually really nice here. Quandary 2 is really efficient, and the amount of space it uses is pretty efficient too, right? Observe that even though we make 2 recursive calls at each time, right? Another thing you should note, even though we made 2 recursive calls at each step, we made the problem smaller fast enough such that the total number of recursive calls was O of n, right? That's pretty dope because this actually means that divide and conquer, which this is an example of, is going to produce pretty efficient algorithms because of this property that we're taking the problem and cutting it down by 1/2 or 1/4 or whatever each time. Yeah, this is a divide and conquer algorithm. Someone asked in chat. All right, so let's go ahead and move on to our next topic. Everyone take a deep breath with me. And type MergeSort in chat if you're ready to learn or review MergeSort. Let's see if we can get everyone to type MergeSort here. Can we get like 50 people to type it? right? I just want to make sure everyone's tuned in and ready to go. Obviously, it's your responsibility to pay attention in class, but it's nice to have some reset points, which is what we're doing here. All right, so let's go ahead and take a look at MergeSort. MergeSort has some intuition here, which hopefully you've seen in the past. It's going to be a sorting algorithm that is actually used in real life. MergeSort is as good as Quicksort, if not better. And a lot of programming languages, for example, Java, their built-in sort is based off of MergeSort. So the reason why we were learning it here is because it's actually used in real life, right? So the MergeSort is going to be a recursive function. You can kind of already imagine that it's going to be a divide and conquer algorithm. So the question is, how do we design a sorting algorithm based on divide and conquer? We start with this. We say that if we have a list that's less than 2, then the list is already sorted, right? Because if you think about it, if I have an empty list or a list of size 1, right? If I have a list that looks like this, it doesn't matter what the number is, right? All of these can be considered sorted because there's only one element, so there's no basis for comparison. Likewise, the empty list should also be considered sorted because, it's the empty list, right? An empty list, we're just going to say by definition is sorted. Otherwise, we're going to take the list that we got passed in that's bigger than size 1, and we're going to divide it into a left half and a right half. And then we're just going to call MergeSort on the halves. All right. If you've seen this before, hopefully this is just a refresher. If you've never seen this before, prepare to have your mind blown, right? Because the trick is somehow MergeSort will sort the left half and the right half magically for us. They're already sorted by the time we're done with this step here. And then once we have the sorted left half and the sorted right half, we're going to merge them together into one big sorted list. All right. And the way we're going to do this is we're going to look at an example. Here's an example, right? I have a list here. It has 38, 27, 43, 3, 9, 82, and 10. It's obviously unsorted. We're going to try to split this in half. We're going to take this list, and since it's not less than 2 elements in this list, we're going to split it into a left half and a right half. So the left half looks like this, and the right half looks like this. Once there's an odd number of elements, we just put the odd number in the left half, right, in this case. Then we're going to split this up, each of these lists, into 4 separate lists. So in the left half, we're going to make smaller lists here, and the right half, we're going to make smaller lists here as well. Go ahead and take 15 seconds. What does the left half look like? What are the 2 recursive calls that will take this list and split it into 2 smaller lists? Right? It says divide the left half and the right half up, and then recursively sort the half. So I'm just asking you, if this is the list that we care about, what should be the left half and the right half? Go ahead and type in chat if you have it. It's going to be 38 and 27, and that's it, right? And then we're going to have 43 and then 3. We're not going to sort these. We're just going to leave them alone, but we're going to go ahead and do this division, right? And that's just to make sure you're understanding and following along with the example. If you have questions or if you're stuck or if you're not sure what we just did and why everyone's typing what they are in chat, feel free to ask and get clarification. All right, so at this step, we do that dividing. We divide into 38 and 27 as the left half here. And then the right half we're going to do is 43 and 3. And on the other hand, eventually what we're going to do is we're going to call merge on MergeSort on this left half here, which is 9 and 82. And then the 10 is split off on its lonesome here. We're going to do one more split. All of the elements that have 2 elements inside, all of the lists that have 2 elements, don't hit the space case. So we split and divide into even smaller elements, right? So now you can see that every single list is actually just a list of one element. The list with 38 in it, the list with 27 in it, the list with 43 in it, the list with 3 in it, so on and so forth, right? At this point, here's where we start merging, right? What we're going to do is we're going to take these 2 elements here, right? 38 and 27, and we're going to glue them back together. Since we know that 27 is smaller than 38, then the 27 is going to go first, and then the 38 is going to go next, right? Likewise here, since 3 is smaller than 43, 3 goes first, and then 43 goes next. Same thing here. 9 is smaller, so it's going to go before the 82. And then 10 is just going to be brought down on its own, right? So again, 27, since it was the smaller of the two, goes down first, and then 38 goes down after it. 3 goes down first here, and then 43 goes down after it. And then 9 goes down here, and then 48 goes down after it. And then 10, being the lonely person it is, gets brought down on its own. All right. Now, let's go ahead and think about what we need to merge next. This is like the elements that we need to merge next. Let's just try to do this manually. What number do we put into our new list first? What's the first number that gets brought down here? Type it in chat if you have it. Between these two lists, we want to bring down the 3 first, right? Because that's the smaller of the two lists, two elements. That means the 3 is being used. And then we need to bring down the next element. Go ahead and type in chat. What's the next element here? 27 is the next element, right? So we compared and we found a way to say, okay, 3 was the smallest element. That goes down first. The next smallest element is going to be the 27. And now we have a 38 and a 43, right? Obviously, 38 is the smaller of the two, so that gets brought down next. And then 43 gets brought down at the end here, right? So there is some step here, this last step here where we have the sorted left, the sorted right, these two green lists here. We have to merge them together based on the smallest elements being brought down first into the resulting list. And that means that overall, there is some algorithm that we have to think about when it comes to merge, right? So this merging happens on the left, this merging happens on the right. We just bring down the elements that are the smallest as we go. And let's just do this one more time so that we are being very, very, very detail oriented here in order to do this one last merge. We have 3 here, we have 9 here. Which of these goes down first, the 3 or the 9? Right, 3 goes down first, which means we bring down the 3 as our first element, and we go from considering 3 to considering 27, all right? Now we compare 27 to 9. Which of these two are the smallest? The 9 goes next, right? So we're using the 9, we bring it down, and then we go and look at the next element, because since they're sorted, we just go from the left to the right, and we compare the next left element on this list and the next left element on this list and see which of them are good, right? So in this case, 10 is going to be better than 27, so we move on. And then we compare 82 against 27. Obviously, 27 is going to be better than 82 in terms of it being the smaller of the two elements, which means we move on to 38 compared to 82. 38 is going to win out, so I'll just bring this down. Sorry for my crappy handwriting. I'm using a mouse. 38 beats out 82, so 38 is used. 82 stays here. Now we finally compare 73 and 82. Sorry, 43 and 82. 43 wins because it's the smaller of the two. And then 82 finally gets brought down on its own. And that's the resulting list all sorted. So there's this merge step that we just manually went through that creates this resulting list, right? We take 2 sorted lists and we make one big sorted list from it. All right. So that's the intuition here. Let's go ahead and take a look at some of the code. MergeSort is one of the last sorts we see because it is actually a lot of code. The first thing we have to do before we even consider MergeSort is how to take 2 lists and glue them together, right? We just did that here manually, where we took this list and found a way to combine them by taking 2 pointers into these lists and moving them along toward the right. Every time we find a new list that we have, a new element that we want to bring down here, we increment a pointer. And here's the code that actually represents that. Merge is an algorithm that takes in 2 sorted lists, L1 and L2. And it's going to output a L3 that contains the elements of L1 and L2 in sorted order. I'm going to give you some time to think about the best case, the worst case, and the average case. And then we'll go through it together and try to analyze it together, right? Again, there is no shame in not knowing, but what I want you to do is try to read this function. I'll give you about 2 minutes here to read this function. Try to understand what it does, since there's a lot of code here. And then try to figure out what the best case, the worst case, and the average case is. The first question, if you don't know how to start, is What is in this case? How do you even define in, right? So I'll give you time to think about that for yourself. I'll give you 2 minutes, and then I want you to vote here, right? You're going through the process of analyzing the runtime here and trying to figure out what is the best case, the worst case, the average case, and how much space does it use. You've got about a minute left, and more than half of you haven't yet voted, which is okay because this is definitely hard to understand, or it could be hard to understand. I don't know if it's hard for you, but definitely try to take a look at this and look step by step about, how many times do you think the while loop is going to fire? What is the point of I and J? What are the runtimes of all of these options or steps in the middle here? And try to use those questions to help you figure out the overall runtime. Is this the entire merge sort? No, this is only the merge step. This is only the last step we saw in the previous slide. I'll show you the code for merge sort in the slide after this. Okay, there's still about 15 of you who haven't voted. Go ahead and give it your best guess now. I'll give you about 10 seconds to put in your answer. Go ahead and wrap up now. Put in your best guess. Again, there's no penalty for guessing here. I just want to see where the class is at. Can we get to 90%? There's only one person that needs to vote. All right, nice. So here's what we got. Most of you think the best case runtime is O of n, though the worst case runtime is going to be O of n as well. And same with the average case, and the amount of space being used is going to be O of n. And thankfully, that's correct, right? There's no scariness when it comes to this algorithm. You just have to understand what's going on. So the first thing I want you to do is take 5 seconds, type in what you defined in as. Go ahead. I know someone already put in their answer, but if you had a different answer, please put that in. And let's figure that out now. Type it in. What's the definition of n in this case? How do we define n? N is equal to the size of L1, so L1 that size, plus L2 that size. Nice. Yeah, so what we want, and this will be obvious once we actually look at what the algorithm is doing, but we need to figure out what n is, and defining that really is a combination of understanding what the function is doing, as well as just kind of thinking about what the obvious thing is. So the obvious thing is that we have a list 1 and a list 2. And if we're going to combine those two into a list 3, then the size of list 1 and the size of list 2 probably matter for the overall runtime, right? So we want the sum of the two sizes in order to define n. Now, how do we actually analyze this? I said that the runtime for all of this is going to be O of n, right? All of these things are going to end up being O of n, and we have to understand why that's the case. So the first thing I'll have to do is figure out, okay, well, all of this takes constant time, right? I don't care about any of this. The while loop is really where things get tricky, right? One thing you want to note when you're looking at the while loop, we have some I and we have some J. We're going to use it. We're checking to see if I is less than L1 dot size and J is less than L2 dot size. If either of these are true, then we're going to do the while loop, right? And if you look inside, even without understanding exactly what's going on in the code, we see that J is being incremented by 1 and I is being incremented by 1 in all of these cases. So what we're saying here is I is equal to the index into list 1, J is equal to the index into list 2, and we're moving them forward one step at a time, right? That's something that you should have understood if you were analyzing this function. At least this is how I think about it when I first start, right? You don't have to be a master at this. Obviously, some of you might feel a little bit less familiar with how this is supposed to go, which is why we're taking so much time in explaining it, right? If you don't know, now you have an opportunity to learn, right? So we know that I and J are going to be indexes into L1 and L2. What do we do with them? We check to see if I first is greater than or equal to L1 that size. If that happens, this is really checking to see, do we have any elements of L1 left, right? This first if check is saying, do we have any elements of L1 left? If there are not any elements left, if no, then add elements of L2 into L3, right? This is saying we ran out of list 1, this first if statement. If we ran out of list 1, then add some element of list 2, so L2 of J, right, into list 3, and then we just increment J. You can imagine, for example, if we said merge on the empty list and then 1, 2, 3, what we would want the result to be is 1, 2, and 3, right? And so this code is saying the first list is empty now, or we ran out of elements in the first list. So just blindly add from the second list and make the J counter go up by 1, the J index go up by 1 each time, and so on. That's the first if statement. The second if statement, this else if here, does the same thing, except it does it for L2. Same as above, but for L2. If we were to have a merge that ran out of elements in L2, right? There's nothing in L2, but there is stuff in L1. We still want the answer to be 1, 2, and 3. But we're saying here, okay, J is either already, like, we're looking at either an L2 that's empty, or J has already been incremented to the point where it no longer has elements. Therefore, just continue to add the remaining elements of L1 until L1 runs out as well, right? If you look at this if statement, it's saying keep going until both I and J are exceeding or equal to the size of L1 and L2, respectively, which means that we are trying to use I and J until we run out of elements. Otherwise, if the current element at I is less than the current, or less than or equal to, rather, the current element at J, add L1s of I to my final list, and then increment I, right? So if the current element needs to be brought down, which is what we were doing in the previous example, right? If you remember from the last example, we compared two elements, 3 and 9. We decided that 3 was the one that needed to be brought down. So we brought 3 down, and then we said, okay, now we look at 27 and 9. The way we moved from 3 to 27 was by incrementing the I. And the same thing is true here if L2 is actually larger than L1. The current element at L2, is smaller than the current element at L1. Then we do this else case, and then we increment J, right? And so at any point in time, do we ever increment I and J both in one iteration of the while loop? Here's my question for you, right? I'll do it in yellow so that, or purple. Question. Do we increment I and J both in one iteration of the while loop? Yes or no? Go ahead and take 5 seconds. If you understand what's going on, you should be able to get the right answer here. Type it in chat now. What do you think? Do we ever increment I and J at the same time when we're iterating through one iteration of this while loop? This while loop runs once. Does I and J get bigger at once? Okay, we're getting a bunch of no's in chat, right? Because we either hit this case or this case or this case or this case. And any of these if and else if cases, they are all only incrementing either I or J, right? So the answer to this question is no. Which means that the overall runtime of the while loop, this runs in times, right? L1 dot size plus L2 dot size, because we increment both of these indices I and j until they are equal to this and this, right? Runs roughly n times in this case, which means that if everything in here is constant work, everything in the while loop is O of 1, right? Which is true. And we run n times. That means the overall runtime better be O of n. Now, the space argument's a lot easier to make. We just go ahead and say L3 in this case is equal to the empty list, right? And then as we add elements in, well, if it started out empty and we add all the elements from L1 and all the elements in L2, then at the end, when it's full, it's going to be O of n as well, right? Since L3 contains all the elements from L1 and L2. All right. And the best case, the worst case, and the average case, they're all the same because of the fact that, again, we don't have any cases here that would cause the behavior of this function to change given any kind of valid list we could pass in. If we pass in two sorted lists, it doesn't matter if one of them is empty or not, and the other one's big, or it doesn't matter if both of them are big. The runtime here will always depend on the size of L1 and L2, and it will always grow linearly if either of these lists grow in size as well. Okay. Type in merge in chat if you feel good about this slide. Type question mark if you are still a little bit confused. All right. So merge takes in two lists and outputs one big list that's also sorted. Can I explain the space again? Of course. The only thing that takes up space is L3. L3 is a list that eventually will contain all the elements of L1 and L2, which means that L3 is going to be of size n, which is the sum of these two L1 and L2 sizes, which means that at worst, the most amount of space we ever use is when we're done building L3, which is O of n overall. All right, so now here's the code for MergeSort. If you understood merge, you should now try to take your time and understand MergeSort. I'll go ahead and explain it a little bit at the beginning, and then we'll do the runtime analysis afterwards. So the big idea here is that we're going to go ahead and take a look at we check to see if the list is small enough. If it's small enough, then we return the list itself. Otherwise, we find the midpoint, similar to how we did binary search before. And we try to create a left list and a right list by calling the sublist function here. And then call MergeSort on the left list and MergeSort on the right list. And then eventually, once they come back, we'll merge the left and the right. We'll just go ahead and relaunch this poll and try to find the runtime here as well. Right? If you remember MergeSort's runtime from previous classes, you can use that. If you're not sure, go ahead and try to stare at this code and work your way through it. And just to triple check, we end at 1:30, or not 1:30, 4:30 today, right? Yes, okay, cool. All right, go ahead and wrap up. You got about 15 seconds. Give it your best guess here. If you haven't answered, there's so many people typing yes in chat and they have no idea why they're typing yes. I bet you. I'm willing to stake money on this, that people just typed in yes because they thought that I asked the question and they had to like do it for participation. All right, let's go ahead and take a look at the poll. If we look at the results here, people think that the best case runtime is O of n, and then the worst case is O of n, and that the average case is O of n, and the space being used is O of n. All right, so that's a problem because that is not the runtime of this algorithm. In fact, the most important thing you can come out of this lecture knowing is that divide and conquer algorithms aren't guaranteed to be O of n. Right? Divide and conquer algorithms are not guaranteed to be O of n in the best case, the worst case, or the average case. We're going to try to take a look at this. I'll give you a very quick, brief rundown of how this works, and then we're going to go and also take some time and see how we could derive this in another way. So I'm just going to explain this since everyone thought that this was O of n. And then if you get confused, go ahead and rewatch this video. I'll also post some resources online to do the runtime analysis. But what you need to know is very similarly to what we had in the quicksort lecture, we started out with an element of size n, right? We started out with a list. This list has n elements inside of it, right? And the first thing we'll do is we'll split that list into two smaller lists of equal size. And we'll recursively call on the left list and the right list. So these rectangles here represent the recursive calls that you would make. Now, if you keep splitting them in half each time, right? The first layer, we're going to have 2 elements of size n over 2. The second layer, we're going to have 4 elements of size n over 4. The fourth element, the fourth layer is going to be 4 elements of size n over, 8 elements of size n over 8. You can kind of see where this pattern is going. How many layers of recursive calls are we going to make in this case? Go ahead and type in chat. If we know that the problem is getting split up by half each time, how many calls are we going to make? Right? If you typed or are thinking log in chat, then you are correct. The runtime, or not the runtime, but the number of recursive calls we're going to make here this is the number of layers of recursive calls that we'll make. All of the layers here represent a different set of recursive calls, right? The first one is the first call we ever make. The second one are the 2 recursive calls we make that split the list into half, right? Each half goes into a recursive call. Then there are 4 recursive calls, each with 1/4 of the list, 8 recursive calls, each with 1/8 of the list, so on and so forth. Now, if you understand this, and if you remember the work we did to understand quicksort runtime in the best case, if you remember that, then it's the same argument that's being made. If there are log n layers, which represents the amount of work we're doing at each layer, log n layers, and n is the amount of work that's being done at each layer, then the overall runtime for the best, the worst, and the average case is going to be log of n. Forget I just said that. Let me say that again. Since you know that the amount of work being done at each layer is n, and that there are log of n layers, then the best case, the worst case, and the average case is going to be O of n log n. All right? That's the answer for all 3 of these runtimes. Log is the number, it's how deep in terms of calls we make. It's not the actual number of calls we make, because if you see here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 calls in this case. In quicksort, the worst case was n squared, yes, because we didn't always have this divide perfectly into half scenario that we do with MergeSort. MergeSort, we're always guaranteed to divide into half perfectly because that's what it does by definition. Now, in terms of space being used, the space being used here is going to be O of n, because at each point we're going to make a recursive call. There's only going to be 1 from this layer that we ever have, 1 from this layer that we're ever going to have, 1 from this layer, and 1 from this layer. In other words, if you can apply what we talked about when we went over in detail the divide and conquer algorithm here, this time and space complexity that we went over here, and apply it to merge sort here, then you'll know that there's only one recursive call that will remember it at any point in time on the top level, one recursive call that will keep track of the list when the list is n over 2, one recursive call that keeps track of the list when the list is n over 4, and one recursive call that keeps track of the list when it's n over 8 in the worst case. Which means that if we have n on the top layer, n over 2 on the second layer, n over 4 on the third layer, n over 8 on the layer after that, eventually we're going to end up with 2n elements that we have to keep track of, right? 2n list elements, which overall will be O of n. That's the argument for space. Now, we have about 3 minutes left. There's not that much time, so I'm just going to go ahead and very, very quickly show you exactly what another way to derive this. So we're going to go ahead and look at recurrence relations because this is definitely something we need to cover. If you have questions, I'll answer them after class. Recurrence relations are essentially a way of identifying this formula in a recursive function. So given a recursive algorithm, we can create this formula for that if we can identify A, B, and C, our f of n here. A is how many recursive calls we make at each step. B is what is the multiplicative factor that we reduce the problem by. And f of n is just how much work do we do at each recursive call. All right, so in this case, we're going to go ahead and apply that here. How many recursive calls do we have, do we make at each step here? What is A? How many recursive calls are we making each time? Every time we call merge sort, we should make 2 calls here, right? We make a call on the left and a call on the right. Someone asked about why the best case isn't O of 1, because the size of the arguments shouldn't matter. And someone else typed in chat exactly that, and I'm proud of both of you, one for asking and one for answering. For B, we have to move on because we're short on time. What is the multiplicative factor that we reduce the problem by? In this case, we take each list and we divide it by half, which means the multiplicative factor is also 2. Now, the amount of work being done at each level, I didn't explicitly state this, but basically merge, we said, was going to take O of n, right? And then if we think about the sublist, each of these are going to take n over 2, right? This is going to be a call of n over 2, and this is also going to be a call of n over 2, which means overall the amount of work is n plus n over 2 plus n over 2, which is 2n, which means that f of n here should be equal to O of n as well, right? Basically 2n, but we don't really care. We're going to just say f of n is n O of n. All right. Now, if we know all of that, there is a formula called master theorem, which is scary at first, but it turns out it's not that bad, that we can use the A, B, and C that we derived in the previous section to figure out the runtime right away. So we said that the A, the B, and the f of n is in O. Like, here's the answers from what we had before. We're just going to very quickly figure this out. If we had more time, I would ask you all to type in, I'm not afraid of math. Actually, just type that in chat. I'm not afraid of math. I promise you this isn't as scary as it looks, right? Don't shut down just because it's in the end of the lecture. I'm going to post resources on how to understand this deeper. But what you'll notice is that A is 2, B is 2, and if f of n is n, then this k is going to be defined. K is equal to the exponent in f of n, right? So if f of n is equal to n, then k is equal to 1 here, right? Then we can do the math here. We're saying if 2 is less than 2 to the power of 2, then this would be the runtime. But it's not, because if we say 2 is less than 2 to the power of 1, they're not, like, this 2 is not less than this 2 over here. So 1 is false. On the other hand, if we check and say if they're equal, that is true, right? Because we're just plugging in A, B, and K into these equations and trying to figure out if 1, 2, or 3 is true. Since 2 is true, that means that the overall runtime for T of n is n O of n to the power of k, which is just 1. So n times log of n, which implies that merge sort was n O of n log n, or I guess theta actually. But in this case, theta and O can be used interchangeably. I know we're over time, so I'll just go ahead and briefly wrap up. Don't worry about this if you're a little bit confused. I will post some reading resources that you should check out to understand this better. But we're going to go ahead and do takeaways. Divide and conquer is a pattern for recursive algorithms that's usually efficient. It has 2 characteristics. There's 2 or more recursive calls. The problem is being reduced by some multiplicative factor at each call. Merge sort is our second divide and conquer algorithm that handles sorting. Quicksort was what we had before, but the worst case in quicksort is, not as good as merge sort, and quicksort in the worst case shouldn't technically be considered divide and conquer. Recurrence relations in master theorem is a formal way of finding the runtime of the divide and conquer algorithm. We went over it in very short amount of time, so if you're a little bit confused, don't worry, I'll post some reading. It's okay to just memorize and follow the formula, and once you do that, you'll get free points on the exam, basically. And quiz 3 is this Wednesday and Thursday. It'll be on sorting, it'll be on quicksort, it'll be on heaps and heap sort, right? Sorting properties, quicksort, heaps, and heap sort, right? I don't think we went over heap sort in detail. So what you'll need to do before next lecture is to watch the last 10 or 20 minutes here. And also we'll have some reading for divide and conquer, which I think will be important for you to read. All right. That's it for today. Thank you so much for your time. Do you know how many people did the survey? I'm not sure. I will check that later this week. Quicksort and MergeSort both have nlog n. In the best case, why is quicksort faster than MergeSort? Yeah, because there are some real world consequences of using MergeSort that involve you using more expensive data structures and operations compared to quicksort that you can do in place using only array operations. All right. If you have any other questions, feel free to ask. Otherwise, we're done for today. Thank you so much for your time. Hopefully you learned a lot, and I will catch you later this week.